Okay, chapter 29, part 1. So we have up until this time just assumed that a magnetic field is present, and we looked at the effect of magnetic fields on moving charged particles. We've looked at the effect of magnetic fields on current carrying wires, which is just a large number of moving charges. In this chapter, we're going to address how magnetic fields come about. So there's one general principle here, right? And that is that moving charge generates a magnetic field. That's why we didn't have to worry about magnetic fields when we looked in electrostatics, because in electrostatics, charges were not moving. But now we're looking at moving charge, and moving charge will generate magnetic fields. Now, that begs some question, because we all know that if we play with a bar magnet, and again, bar magnet has two poles, north and south, and I'm sure many of you during the course of your life might have put a bar magnet under a piece of paper and spread some iron filings on it. And if you haven't done that experiment, you can look it up on YouTube. But magically, surprisingly, one can map out the magnetic field lines. And magnetic field lines, as we talked about before, will start on north poles and end on south poles. And so we can very well imagine that magnetic field lines are emanating out of the north pole and terminating on the south pole, and we can imagine a whole host of these. And so this is what the magnetic field lines would look like, and if you were to actually put iron filings on a paper, which is over a bar magnet, you would see that the iron filings trace out pretty much a shape that I've just determined, or I just drew on the iPad here. So, but the question then that is being begged to be asked is, where are the moving charges? Where are the moving charges? Clearly, the bar magnet's not connected up to a source of EMF or voltage. There's no current. That's evident. And so, where are the moving charges? And so, this goes back to trying to understand the history of magnetism, electricity, and how they're conjoined. So, up until 1820, electricity and magnetism, electricity and magnetism were pretty much thought to be a disparate phenomena. And again, you can understand that. I'm going to upload a couple of videos that I made in the lab a little bit later as we get into this discussion, but you can very well understand that if you're playing around with bar magnets and seeing their mutual attraction, their mutual repulsion. There's nothing about that that suggests that electricity is involved. And likewise, right, if you were to connect a battery to, to a circuit or a wire and generate a current, there's no direct visible evidence that magnetism is involved. But in 1820, Hans Christian Ørsted accidentally did an incredible experiment, and we're gonna redo that experiment, and I'm going to show you basically the results of that on an isolated YouTube. So it'll be called, what did I call it now? I called it magnetic field wire, and there's going to be 2 of them. So you should check those out, right? So check out the YouTube videos that I'm going to upload along with this lecture. But let's go back even deeper in history. And so the first material that demonstrated, or the first found material that demonstrated magnetism, was the mineral magnetite. And magnetite is really a very interesting mineral. It was one of the first minerals whose structure was solved by X-ray diffraction in the beginning parts of the 20th century. So magnetite has the molecular formula of Fe3O4. And if you try to work out the oxidation states here, you'll run into a little bit of a problem unless you are clever and you realize that there's an Fe2 plus, there's 2 Fe3 pluses, and there's 4 O2 negatives. So again, that's not apparent just by looking at that molecule, but that's how that's worked out. Okay, and again, the crystal structure of this is what is called a reverse spinel. And again, for those of you who are interested, can look up the spinel structure, and then hopefully you'll be able to better understand what it means to be a reverse spinel. So magnetite, or what is in the historical record called a lodestone, was among the first magnetic materials discovered. And so, so let's take a look at this, right? That's most of you know a bit of chemistry. And so if we look at iron in the 0 valence state, iron is Z26. And if we were to look at the electron configuration, it would be 1s2, 2s2, 2p6, 3s2, 3p6, and then the 4s2 fills before the 3d level. As a matter of fact, the 4s level is really close in energy to the 3d, right? Really close in energy. But most chemistry texts will write it as 4s2, 3d6. And so this then is an argon core. This is an argon core, 4s2, 3d6. Okay? And if we were to look then at the ferrous ion, then that would be an argon core, and that would be 3d6 because the 4s2 electrons are lost before the 3d6. And then if we were to look at iron 3 plus, the ferric ion, then that would be an argon core 3d5. Now, you remember that there are 5 d orbitals, right? So there's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And so now, according to Hund's rule, right, in the ferric case, we know that these electrons are all going to go into a single orbital before pairing up. And the reason for that is ostensibly simple. It's because the electrons in separate orbitals are farther apart, less repulsion, and it reduces the energy overall of that configuration. And then the 3d6, we would fill each of the 3d orbitals separately, and then we go back and pair them up. Now, you remember, I hope, the notion of electron spin. So electrons have an intrinsic spin angular momentum. Now that's a mouthful, okay? And so early on when this was first discovered, and we don't have enough time remaining in the semester to go through the beautiful story of electron spin. But the early people who looked at this actually thought that the electron was able to spin about its axis. Okay, so we actually had a spinning electron. Now that's actually turns out to be very false, right? Very false. And so most, at least introductory chemistry books that picture this spinning electron, try to put that baggage out of your mind, because that is not what's happening. But there is an associated angular momentum. And when we talk about angular momentum, as you will recall, we're talking about objects that are rotating. And so it was a very natural follow-up that if the electron has an angular momentum, then something must be rotating or spinning. And that picture is very murky, but the electron itself is not spinning, but it has an associated spin to it. The spin quantum number is 1/2, and most of you know that could be either spin up or it could be spin down. Okay, and so that when we go back and we talk about filling orbitals like that, we're talking about putting electrons in those orbitals such that they're either spin up or spin down. So we think of the electron now as a moving ball of charge, a moving or rotating ball of charge. So there's your moving charge. It's not really rotating, okay? And it does have an angular momentum. And as a consequence of that, it generates magnetism. It generates magnetism. We say that is a magnetic moment. And again, that discussion is far beyond the scope of this course, but for those of you who want to take modern physics, we will go into this in great detail. So there's your moving charge. So within these ions are electrons in d orbitals, and those electrons have an associated magnetic moment. And in these crystals, these magnetic moments align. and they align in such a way in what are called domains that they can be permanently magnetized. Okay, so so again, how that comes about is beyond the scope of this course, but within the mineral crystals of magnetite, there are these larger domains where all of the lattice, the crystal lattices are oriented in the same direction, and hence all of the spin magnetic moments line up, and they form bulk magnetism. So that could be easily destroyed, usually by just heating a mineral like magnetite up. Heating it up will kind of jumble the orientations of the magnetic moments within those domains, and it could lose its magnetism. Okay, so there's your answer. You do have moving charge. The moving charge is coming from electrons in the d orbitals. Okay, but we're not going to address that. We're going to look at charges moving in more conventional wires. But before I leave this opening discussion, there's a couple of things that I want to point out to you. Is that you should spend some time, for those of you more biologically inclined, there's a field called biomagnetism, and certain bacteria can actually form magnetite crystals. Magnetite crystals within their cell body, and they actually use this for sensing Earth's magnetic field, and they use it for being able to move in a particular direction. And so they can actually sense Earth's magnetic fields, and how should I put this? Move preferentially in one direction. Likewise, there's birds that have magnetite in some brain tissue, and likewise they use this for navigation by sensing Earth's magnetic field. And these are really pretty cool applications of magnetism in organisms. Even humans it's been discovered that even humans can form magnetite in their brain tissue. So again, it's not inherently obvious that we are sensing Earth's magnetic field, but who knows what goes on subconsciously, right? So cool. Anyway, I'm going to end that opening discussion for generation of magnetic fields. We'll get into more of the material of chapter 26, but I just wanted to tease you with some more of the interesting aspects, both chemical and biological. So very good. All right, stay tuned.